Okay, so I would like to probably define some things first before we move on. First point that I want to note is I want to describe the conformal time, which is essentially one of the co-moving coordinates, but for time. And the way we define conformal time is with eta, and I relate it to the proper time t with the scale factor. Okay. And also I want to remind you of the picture that we had last class. So you remember that I drew this particular dotted line for the early universe, where I didn't really define what the early universe was. So in that case, what I showed you was just this bit, right? Where we had the evolution of the universe. Where we had the evolution of the universe given by where's the highlighter? This particular part, right? So essentially we had a distinction between radiation domination. So I'll just write it as rad. Another distinction for matter domination, and this is where we are today in the cosmological constant era, or you can say cosmological constant dominated era. Okay. Now, for us to essentially understand what this evolution of the universe is, we need to understand what are the underlying initial conditions that left this evolution, right? So we need to have a picture of this area over here. So now in this class, we will try to bridge the two phases. So we will try to understand how we can find certain initial conditions that will give rise to the evolution that we see today. So today we go back in time. So we go back to the very beginning of the universe and try to postulate how the conditions of the beginning of the universe led to the universe that we see today. But first, to understand what these initial conditions are, we need to understand what Big Bang cosmology is, right? And Big Bang cosmology is essentially everything that has happened from this part to where we are today. Okay? Now, in generic Big Bang cosmology, we understand a few things. We have expansion of space-time. So we have this universe that is expanding. We have radiation domination, matter domination, and the cosmological constant domination that we see today. And we know that since the universe is expanding, something is expanding with the universe, right? What is that something? So let's try to understand that first. Now, in regards to how we understand that the universe is expanding is by just looking at things that are far away, right? So for example, if I'm here on Earth and I'm looking up at the sky, if I can see, let's say, a collection of stars today, and a week later I see more collection of stars, then I will know that the universe is expanding, and therefore my view of the universe is expanding with it, right? So since everything in the universe, at least not everything, but at least light or any signal that is transmitted in the universe travels at the speed of light, that means if the universe is expanding, those transmissions are also expanding at the speed of light with it, right? So essentially what I'm trying to say is that, let's say I am here, and this is the universe that I can see today, okay? Again, the universe is not a circle, but just for understanding, I'm writing this is a circle. So let's say these are the collection of stars or parts of the universe that I can see today. If the universe is expanding, my view along with the universe should also increase. So if I can see this much today, I should be able to see more later on. Right? That makes sense. So essentially, that means this particular bubble of my vision, observation, is being expanding with the expansion of the universe. So if that is the case, then if I can indeed see, let's say, the the cosmic microwave background, the CMB today, That means at some point it was outside my vision, right? Because from this idea, I can understand that আমি যতটুকু আজকে দেখতে পারি পরে আরো বেশি দেখতে পারবো, because my vision is expanding. So if I go back in time, that means my vision would shrink and I would see less going back in time, right? So if I can see the cosmic microwave background today, that means at some point in the past I would probably not see it. Does that make sense? So in that particular explanation, when I look up at the sky right now, I see, when I look at the CMB background, and remember that the CMB background is the farthest that we can look in the past timeline of the universe. When I look at it, I see that they have something very coherent with each point in the CMB background, that is temperature. We see that the temperature of the CMB at particular points are the same. Now, if you go back to your thermodynamics class, how does points become same in temperature? So being in the same temperature means that they're in thermal equilibrium, right? And you can only be in thermal equilibrium if you have thermal contact, right? Zeroth law of thermodynamics. So if that is the case, that means they must have been in some sort of thermal contact before for them to have such coherent temperature today. But essentially, if you look back at the CMB, at that particular time, they were not supposed to be in contact because they were outside the particular observation bubble. And by observation bubble, I can also term it as causal contact. So they were outside each other's causal contact. Do we understand what causal contact is? So let's go back to understand what causal contact is. So let's say this is a light cone, okay? And we know that light cones depict space and time coordinates. So this is a very bad drawing of a light cone, but let's do this for our understanding. So this is how space traverses, and this is the direction that time traverses, right? So if I am here today, everything that I can be in causal contact with will be inside my light cone, right? I can only travel in time-like curves, which is in the direction of time. I cannot move in space-like curves because for that I need to move faster than the speed of light, right? Which is not possible by the postulate of special relativity. So in that case, everything I will be in causal contact with will be inside my light cone, inside this particular area, right? So everything that exists outside will be outside my light cone, and therefore I will be out of causal contact with them. Okay, so for me to be in connection or basically interact with anything that is outside, I have to violate causality. So if I want to draw this picture for, let's say, the universe, okay? And let's say this is the time where I can see the CMB, which is also termed as recombination era. And let's say this is the initial starting of the universe that I term as the Big Bang point, right? So this is called T. Let's just say this is T equals to 0. When there was no time, there was nothing, just that particular point that we think started the universe, right? So let's call this the Big Bang singularity. So let's say if I have particular points in the CMB, they will have their individual light cones, right? And I am over here somewhere where I denote this as T naught. And remember, T naught, the subscript naught in cosmology stands for everything that's measured today, right? So this is at present. Okay. So from here, if I exist at the present line, my light cone will cover all the little points during CMB, right? So that is essentially why I can see the CMB from here, because it is in causal contact with me and I can observe it. However, if you go back in time, and if you were here, particularly, let's say, this is your light cone, right? And of course, if this is the Big Bang singularity, the light cone does not extend, right? It stops over here. So this particular light cone is not in causal contact with this particular light cone. They are not coming in any sort of interaction. So for these 2 points to be in thermal contact, and remember, thermal contact gives you thermal equilibrium, is somewhat impossible, right? Because if they're not causally connected, that means they don't have any sort of information change. How do these individual points know that they have to be the same temperature? They don't know that. And for all of these points that are not causally connected, how are they in so much coherence? How are they the same temperature? So that is a puzzle in cosmology that Big Bang cosmology or this particular model that we've seen does not answer. And this is called the horizon problem. Okay. Now, there is another problem of Big Bang cosmology, which is essentially from observation. And we see that when we have observations, we sort of can make certain measurements of how flat the universe is. Okay. And when we observe it, when we measure it, we see that the universe is pretty flat. Okay. Now, it is so flat that the energy density that comes from curvature is almost negligible. It's like almost zero. So the question is, flatness or this particular condition of flatness is very fine-tuned, right? Because let's try to understand what happens. Remember my lecture when I was talking about three possible geometries of the universe? You can have flatness, you can have spherical S3, you can have hyperbolic geometry H3 and all of that stuff. So how I depicted that was with two marbles, right? So if you had a flat space and you had two marbles to move parallelly, they would always move parallelly because nothing would be deviated. If you had spherical geometry, they would converge. And if you had hyperboloid geometry, they would diverge, right? So now being parallel or staying parallel that way is a very fine-tuned condition, right? When you have to sort of hit a critical spot for it to be exactly the same all the time. But this particular critical spot is what the universe hit. And how is that so? Like, how did the universe, with its chaotic environment, chaotic dynamics, and all of these, small things that can deviate it from flatness, still remain flat? That's a question, right? And that particular question has not been answered by Big Bang cosmology, and we call that the flatness problem. So there are more problems that Big Bang cosmology does not answer. Maybe I will not discuss it in class, but I can, name one, which is called the monopole problem. And the monopole problem essentially states that why don't we see magnetic monopoles in the universe? We have electric monopoles. What I mean by monopoles is that you can have a singular electric charge that creates a field, right? However, we don't have that for magnetic monopoles. We don't have a singular magnetic charge that creates a field. You always require a magnetic dipole. You need north and south. You can never have north. Even if you have a magnet, you cut it in half. Let's say you have a magnet like this, north and south ends. You cut it in half. This particular half will still build another dipole, north and south. So in nature, we do not see magnetic monopoles. And from a universal perspective, you should question this, right? If we have electric monopoles, we can have singular charges, and they create fields, and electricity and magnetism are related, right? Why don't we have magnetic monopoles? So that is a question that Big Bang cosmology does not answer. Where are the magnetic monopoles that we should see in the universe? So let's revisit the horizon problem now, but more mathematically. So for me to explain the horizon problem, I need to define the horizon, right? And particularly in cosmology, we have something called the particle horizon, which is denoted by dh, which is a function of the conformal time, and it is given by the following expression. Okay. And this, I can write it from Ti to T, some arbitrary T, where Ti is essentially your initial time that you're starting with. Now, if you want to start with the beginning of the universe, you can set eta I to 0, and that would mean that the particle horizon is just a function of the conformal time. Okay, so this makes using conformal time very easy, because now what is the particle horizon? The particle horizon is essentially what we are causally connected with, right? However, observation that we can make of the past. So in that case, if I can sort of parameterize this with the time that elapsed between that particular point in space that I can see in the past to me today, it makes my calculations much simpler. Now, From here, I can also reparameterize this and write it in terms of something which you will see in a bit. And I can reparameterize my A's and T's in terms of the scale factor. And write it as the following. And I can take a logarithmic limit and express my particle horizon with a factor that is H inverse. Okay. Now, why is this important? Because this particular H inverse is called the co-moving Hubble horizon or co-moving Hubble radius. Okay, and we will see that particularly during early universe mechanisms, we use this notion H inverse to be the causality boundary of whatever we can see, whatever we can observe. So here I'm defining H inverse as the co-moving Hubble radius. And this will be essential when we explain the horizon problem further. Okay, now here AI, when I set it to 0, this essentially gives me what? This would give me the Big Bang singularity, right? So remember when I was explaining the scale factor, I said that the scale factor can range from 0 to 1 today. Right? So that means that there is a particular point where A could be 0. And what happens if I put A 0 over here? There's a problem, right? I have a 0 in the denominator. That means it gives me some sort of singularity, right? And therefore, that is the Big Bang singularity I'm talking about, where A equals to 0 is some point in time where I cannot devise the physics. What is happening at that particular point? So again, going back to my picture, A equals to 0 exists here. Okay, at the very beginning of the Big Bang model that we have, the Big Bang cosmology model we have. So this is a problem, number one. Horizon issue, J, how is the CMB, so in thermal equilibrium if they were causally disconnected? Another issue, why is the universe so flat? Why does it abide by such a special and critical condition? Still today, even after so much evolution, that is another question that Big Bang cosmology doesn't answer. So in order to have an early universe model, again, remember what we're trying to do is trying to find something that fits this part, right? So that we can explain this part. So in order to have a model that explains this part, I need to make sure that whatever problem we have over here is solved by this particular model. That is what we're targeting here. Okay, so moving on. It is really interesting because if I want to talk about the horizon problem, and let's say you go home, or maybe like in the break or something, you go outside and you look up at the sky. So if this is the sky that you're looking out towards, if you make a deviation of 2 degrees in your vision, let's say I look at this direction first, and I make a deviation of 2 degrees and I look at this direction, those 2 degrees or the separation of those 2 points will still be causally disconnected during CMP. That means imagine the amount of points that were causally disconnected in the sky that you can see today, which is mind-blowing, right? That means at that time in the past, at the very beginning of the universe when the CMB was created, those 2 points just deviated by 2 degrees were not in connection, but they're still coherent in temperature when I look at the CMB. So that is a big issue, right? Why does that happen? It's a big, very, very big question. So let's put that hanging and let's look at the other problem more explicitly. Oh, another note that I want to make, what I mean by being causally disconnected is they were not inside each other's particle horizons. So let's say if I am over here, and this is my particle horizon, I will only be able to see what is inside my particle horizon, right? Now, if anything exists over here, I will not see it because it's not inside my particle horizon. Let's say there's another body over here who has their own individual particle horizon. this particular body and myself will be causally disconnected. I will not be able to interact with them because they do not include, I am not included in their particle horizon and they are not included in my particle horizon. Okay. So what I mean by 2 points in CMB being causally disconnected is this is 1 point in CMB and this is another point in CMB, but somehow they are in thermal equilibrium. And again, iterating it, thermal equilibrium can only happen if something is in thermal contact with each other, right? Because if you put two bodies together, one is hot, one is cold, they will come in thermal contact. If they're away, they cannot, right? So that means if they are causally disconnected, no information, no interaction happening, how are they in a situation where you require that contact to be? Okay, so that is the problem. Now, moving on to the flatness problem. And to explain the flatness problem, I need to define something called the density parameter, which essentially gives me a ratio of the energy densities, if you remember rhos, right, from the energy momentum tensor. Now, this density parameter is given by rho. Okay, so this is the rho or the energy density that we have in the universe. And this is rho critical, which is essentially the energy density that you would have if the universe was just flat. Okay. So I can write this density parameter using, what is this called? Omega. And this omega can be divided in two parts, which I call as lambda naught and lambda k. Okay. Again, remember what naught stands for, right? Any energy density parameter that I can see today. So essentially, this should be energy density parameter that is given by the constituents of the universe, right? And the constituents of the universe is depicted by radiation from the radiation domination era, matter from the matter domination era, and cosmological constant, right? Or dark energy, whatever. And omega k is essentially coming from curvature. Okay, so we also understand that curvature can amount to some sort of energy density that we've seen through the Einstein's field equation. So if I am to depict the overall density parameter, I should also include a curvature term, which comes from the Kc term. Remember something like this? I don't quite remember. Something like this, right? So this particular term will amount to the density parameter. This comes from the Friedmann equations, if you remember. So there is one term with k dependence, and k is for the geometry. Remember, k equals to 0, 1, and minus 1 for the geometry. So this will amount to the density parameter over here. Okay, so to understand the flatness problem, I need to see how much of the density parameter is indeed influenced by curvature, right? So যদি আমার curvature প্যারামিটারটা অনেকটুকু density প্যারামিটারকে কন্ট্রিবিউট করে, তার মানে আমার curvature exist করতেছে. But if that is negligible, then I will understand that energy contribution from curvature is negligible. Therefore, it depicts a flat universe, right? So from here, I can devise a sort of expression for omega k by considering that rho critical is given by 3m Planck squared h squared. And I plug this in over here. And what I will get for an expression of omega k is the following. So any subscript with 0 means that I am considering it to be today. Okay, the measurement or whatever function I have is being theorized or calculated today. So in this case, we use, to depict this, we use the fact that rho critical is proportional to h squared, and rho critical minus rho is proportional to a inverse squared. Okay. Now, from observation, we in fact see that this particular term over here, which is a measurement that we can take today through telescopes, satellites, and all of that stuff, is very small. it's almost negligible, and it has a particular value which is less than 0.00. So that makes the universe pretty flat, right? Because the contribution from curvature is almost negligible. Now, you understand that the universe is expanding, right? And you remember that I depict the expansion using the co-moving Hubble radius, which is given from here. So that means that AH inverse is increasing, right? That means if I take a temporal derivative of this, I should get something that is positive because it's increasing, right? So if this is increasing, then it would affect this expression over here, and I would see that indeed if the curvature contribution is 0.005 today, it must have been much, much smaller before, right? So in that case, the universe started out flat. But how? What were the initial conditions that led to such flatness of the universe? Like you could think, okay, the universe is expanding, maybe some physical mechanism led to the flatness today. But from this perspective, we see that the universe started out flat. Why? Right? So that is the flatness. Okay, now since we have all of these problems, now we have to target these problems and try to find a solution that gives rise to the not only the solutions to these problems, but also a model that can answer how the universe began, right? So these particular initial conditions will depict the universe's starting and also solve these particular problems of Big Bang cosmology. So we need another model of the universe. So we see that most of these problems are well, not it's not singular to the fact that the universe is expanding, but one of the key attributes of Big Bang cosmology is that the universe's co-moving Hubble radius is increasing, right? So let's try to reverse that. Let's try to see what happens if I take the opposite, okay? If I consider that the universe's co-moving Hubble radius is not expanding, but let's say it's shrinking, okay? Let's see what happens then. So that means I have to depict that this is negative, right? Because if this is negative, that means that co-moving Hubble radius is in fact shrinking. So if that happens, and remember AH is equal to A naught by A dot by A. So in that case, I can write AH to be just A dot, right? So essentially d by dt is over A dot inverse. And if I find this out, I would get something like this, right? And if I say that this is negative, this must imply that this is positive, right? Does that make sense? Because this is a square term, this is inherently positive, right? And to maintain this negativity, this particular term has to be positive. This is where I come up with the idea that in the very early universe, we must have an accelerated expansion to solve the horizon problem and the flatness problem and many other problems that Big Bang cosmology has. That means we need a model with an accelerated expansion. Number 1 point to counter Big Bang cosmology. Let's see if this indeed solves the problems or not. So let's revisit the horizon problem, where we have the particle horizon given by the following. And remember, I can say from here that I can sort of make a similar relationship with the particle horizon and the co-moving Hubble radius, right? Because of this relationship. So from now on, let me just depict the particle horizon as the co-moving Hubble radius. That is what depicts the, again, causality boundary of what I can observe or what I'm causally connected with. So in this case, if I consider that indeed the Hubble radius is shrinking, in that case, I can say that at the very beginning of the universe, or let's say initial point of the universe, is depicted by this particular notion over here, which is AI, just to depict initial values. So AIHI inverse, which is the initial co-moving Hubble radius, must be much larger than age inverse, right? Age inverse is arbitrary co-moving Hubble radius at any given time. Okay. So আমি যদি চিন্তা করি যে Hubble radiusটা shrink করতেছে, okay, during this early universe model, তার মানে of course initially it was bigger than what it is now, right? So it must be bigger and then it shrank and now we see something that is smaller. So therefore initially it must be much larger than what we have today at any given time, right? So this is the condition that we will see in fact solves the horizon problem. So if this is the case, I want to illustrate this further by considering a flat universe. Again, we know the universe is flat. So let's take a flat universe which is dominated by a fluid with some equation of state. So flat universe dominated by the perfect fluid, remember? So dominated by a fluid with some equation of state omega that I defined earlier, that goes by P by rho. Okay, so this is constant omega. So if that is the case, I can find from the Friedman equations a notion for the co-moving Hubble radius, which goes as follows. Okay, now from here I can find the particle horizon just using the expression of the co-moving Hubble radius over here. And what I will find is the following. By integrating it, I will get two terms, which again, remember, I can denote as this from its definition, right? That I mentioned somewhere over here. Okay. Now, so this is the notion that I have of the particle horizon, given that I have a shrinking Hubble sphere. Now, okay, so I did not imply that I have a shrinking Hubble sphere yet. I just, solved it from the Friedman equations, plugged it in the particle horizon. Let me now imply that I have a shrinking Hubble sphere. Okay, so if I imply that I have a shrinking Hubble sphere, that means implying this particular condition, I will see after I set eta I equals to 0 for AI equals to 0, we will get something that is equal to conformal time. Now, we know that ordinary matter abides by something called the strong energy condition. Okay, so if I have ordinary matter, and this is just, I'm just throwing out this information because I will use it in a bit. So for ordinary matter, it abides by something called the strong energy condition, which is shortly said to be SEC, which is given by this particular constraint. And this essential energy condition is what makes the expansion of space. Okay, this is what makes, an expanding space time. Now, we are sort of countering this, right? We're sort of countering this idea that space is expanding. We say that space is not expanding, but now we have a shrinking Hubble sphere. So in that case, whatever that is, dominating in the early universe must contradict this energy condition, right? So it must break this energy condition. So whatever, let's call it, I don't know, let's call it something. Okay. Something breaks this energy condition. So therefore, that means that 1 plus 3 omega is now negative. Okay. If you plug this in over here, you will see that eta I goes to negative infinity. Okay. And this is interesting because now I don't have a singularity at eta I equals to 0, but eta I is basically shifted towards negative infinity, right? By breaking the strong energy condition. Now, what does that give me? Let's look at that particular diagram again. So now you remember I had recombination era, which is essentially the time at which the CMB formed. So let's call it TCMB. Let me call everything with eta now because I'm reparameterizing. So this is at eta CMB. Okay. And this was supposed to be where eta equals to 0, right? But now eta equals to 0 is not the beginning. It's not the starting point anymore, right? Because I see that eta can go back. Eta can go to negative infinity. So I can have more etas, more eta slices, time slices that go towards negative infinity, right? And this is where I am today. So this is eta naught. So this is present. So essentially what I have over here is, let me draw the light cones of the CMB. And this is my light cone. I can see all the CMB points from where I am today. But remember, the problem was that these particular points in the CMB were causally disconnected, right? Because I have this particular boundary over here at eta equals to 0. But now, let's say I don't have that boundary anymore. I can extend below, right? So that means these light cones also extend. And you see what happens? They become causally connected, right? So that means even if they were not causally connected over here, at some time in the past, they were definitely causally connected, and that solves the problem. That ora causally connected chilo. They could express and interchange information. Maybe some point told the other point, hey, let's be in the same temperature, and they became the same temperature. And now they just got out of causal contact, and we can see the CMB still in coherent temperature, which solves the horizontal. Exactly. Why does that happen? Because the Hubble radius is shrinking, right? So আমরা যেটা চিন্তা করি, যেটা নরমালি আমরা প্রথমে শুরু করছিলাম যেটা দিয়ে, সেটা হচ্ছে this is my, let's say, Hubble sphere, right? My Hubble radius. Now, if it's expanding, it's expanding, expanding, expanding. So what I'm doing is I'm engulfing more things inside my sphere, and I can see more things, right? But now take the other way around. If your Hubble sphere is shrinking, then I would start to see less and less, right? So some point that I may have been causally connected with could be causally disconnected to me inside this particular Hubble sphere. So it makes sense in both ways that if the CMB points were causally connected, if I have a shrinking Hubble sphere, at some point they would go outside their particular and individual Hubble spheres, and you would not be causally connected with them anymore. So this essentially solves the horizon problem. That means having a shrinking Hubble sphere, which in turn gives you an accelerated universe, will solve the horizon problem. So that means we're in the right track. Now let's look at the flatness problem. How much time do I have? I might need to do. Is that okay with everyone? Might need like 10 to 15 minutes more. Okay, so now let's revisit. I'll just cut down on this part a little bit. So now we go back to the flatness problem, and let's see if the shrinking Hubble sphere indeed solves this problem or not. So again, reiterating the curvature density parameter, which is given by the following expression. At any arbitrary t. So now we will see that if any initial curvature decreases, so you have H inverse to decrease, we will see in fact that this will decrease omega k, which is sort of explicit if you look at this particular form, right? When H inverse jodi choto hote thake, then omega k at an earlier time should be small, right? Which makes sense because we start out with a small omega k, and now we have something that's still small, but at earlier times we had much smaller curvature contributions, right? So which essentially solves the flattest problem if we have a shrinking Hubble sphere, but let's look at it a little more explicitly. So again, if I consider the model for a perfect fluid with some equation of state omega, I can rearrange my Friedman equations and I can have an expression as this. Now remember, I'm not deriving anything, but I strongly suggest that you derive everything from the Friedman equations that I gave last class. And also they're on my notes. So we will get an expression that looks like the following. Okay, and if we substitute this in the curvature parameter over here, we will get a curvature parameter, which is an expression of n, which I will say what n is in a bit, as the following. Now, for this particular class, maybe understanding where these mathematical expressions is not important. What we need to know is how this scales, so that we can sort of have an idea of what this is doing to the physics. Now here, n that I have defined is called the number of e-folds. And this number of e-folds is essentially what determines how long this accelerated phase lasted. But I will follow up on that later. But for now, just take it as that. Okay. Now, this particular expression over here has two fixed points. Maybe it's not explicit from here, but once you work it out, you will see that two fixed points exist at omega k equals to 0 and omega k equals to 1. Okay. Now, for people who have not done cosmology, maybe this is not very apparent what this means. But if omega k equals to 0, that means the curvature contribution to the energy density is negligible, 0. Right? That means the universe is flat. Right? Now, what does this mean? Now, for people who have not done cosmology, we have a certain notion where we can write so we can write this as the following. So we have this relationship of density parameter that you can derive to say that, again, reparameterize it and say that this expression holds. Okay. So if omega k equals to 1, what would that mean? That any contribution from here is 0. Right? So remember what omega naught is. Omega naught is the contribution from radiation, matter, and cosmological constant. So if omega naught goes to 0, that means we have nothing in the universe. Right? That means there is no contribution from radiation, no contribution from matter, no contribution from the energy, dark energy, or cosmological constant determination, nothing. So that means the universe is empty. So this is a solution for an empty universe, which is also called a Milne universe. Okay, this is a particular cosmological model that people work in, but it's empty. Okay. So of course, this is not true, because we know we don't live in an empty universe, right? Because we exist, right? So of course, this is a proven fact that the universe is not empty. So therefore, this must be true, right? And therefore, the universe is flat. So this also solves the flatness problem, which is great for us. So that means we need a particular model that is accelerating, has a shrinking Hubble sphere, and takes place before eta equals to 0, right? Because as you can see from here, it should follow in this particular region, which is before the Big Bang singularity. Okay, so now this particular model is called inflation, which satisfies all of this into one particular model where we have an accelerated expansion at the very beginning of the universe. This is essentially what pushes the universe to expand today. So you might ask this question even when we were doing Big Bang cosmology, right? So why is the universe expanding to begin with? Why should anything expand, right, out of the blue? This is what is pushing it. So if you have something that has accelerated expansion, like very high expansion rate, so of course, if it stops accelerating, you would still have some sort of residue speed, right? And that particular residue is what is expanding the universe today. Now, another question to note over here is that, okay, the universe was expanding, right? But then it didn't have any sort of acceleration. So let me go back to my picture that I started with over here. So we know that the universe was expanding over here, but it did not have any sort of acceleration. Now we're saying that inflation takes over in the early universe. So this particular time is depicted by an inflationary model. Now, however, we see that we are again accelerating at present times. So in modern cosmology, it's actually essential to answer this question, that we need to find an early universe model that is coherent with observations that we see today. That is, for example, radiation, matter domination, যেগুলো হয়েছে এই পার্টিকুলার টাইমগুলোতে আমরা অবজার্ভ করতে পারি and দেখতে পারি ওদের ফিজিক্স কিরকম ছিল, right? So ওই পার্টিকুলার অবজারভেশনস এর সাথে we need some initial conditions that is coherent with that observation, and also we need to match the initial conditions, the early universe model, to a universe model that we have today, which is late time cosmology. So modern cosmology এখন একটাই গোল, সেটা হচ্ছে early universe model and late time model কে এক করা. Find something that explains not only the early universe but also the acceleration that we see today. Okay, and we're still working on it, and inflation looks like a very good candidate. Okay, so let's now introduce ourselves to this beautiful model that explains all the problems of Big Bang cosmology and gives us a very beautiful early universe model. So to understand inflation, first we need to understand how long did this particular era last, right? Because আমরা একটা জিনিস খেয়াল করছি যে it does solve the horizon problem, it does solve the flatness problem, but let's say acceleration happened for an instant and then it stopped. That would not essentially solve anything, right? So we need an optimum amount of time for this acceleration to last, for us to indeed have the initial conditions we need and solve the problems. So therefore, we need to make an assumption of how long this inflation lasted. In that case, what we need to do is first make an idea of, the Hubble radius that existed during inflation, and make a sort of connection to the Hubble radius that we see today. Because remember that whatever condition that happened during inflation resulted in an evolution to what we see today, right? So there has to be some connection between the two. So we can say as a statement that, of course, the universe today, which exists in some particular Hubble radius, was inside the Hubble radius at the beginning of inflation. Why does that have to be true? Do we understand what's happening over here? So what I mean by this inequality is that, okay, so let's look at this chart. So I know this is true. This is just generic Big Bang cosmology. এখন inflationary time we have the Hubble radius to shrink, right? I did not mention what these bars were. Right? I just drew a diagram to show you. Now these bars are essentially some time component, and this is actually a logarithmic scale of the scale factor, which you can reparameterize as eta. And this is actually, okay, let me not do it with K, let me write it as the co-moving Hubble radius. So basically what you're drawing over here is a plot which relates the co-moving Hubble radius to time. Okay. So if during inflation, which is this era, we have the co-moving Hubble radius to shrink, that means the line should be something like this, right? And perhaps if you've done cosmology, you've seen this everywhere, right? The model of the universe. You go down, Hubble radius shrinking, shrinking, and then inflation stops, and then you have expansion again, and again, we are accelerating. So kind of dips down, but we don't know what happens later on. Okay. So apatot amra ekhane, where we're sort of diving down, but this picture is theoretically more or less there. Okay. So if that is the case, then we must think that wherever we are today, there must be inside the Hubble radius that started during inflation, right? মানে হচ্ছে ইনফ্লেশনের শুরুতে যেটা ছিল সেটার বাবলের মধ্যেই তো আমরা এক্সিস্ট করব, নাহলে তো হচ্ছে there is no point in having the universe to begin with. The universe started out somewhere. Fine, the Hubble radius shrinked, but it expanded again. So wherever we are today, we should be inside the Hubble radius that we began with, right? And that is exactly what this particular inequality states. Okay, so if that is so, well, then we can formulate a couple of things from here. And maybe I will skip on the details because time, but I can sort of formulate a couple of things, which is I can find the number of EFOs, which I can remember is given by the amount of time that this expansion lasted. So I can find a certain relationship of the number of EFOs to understand how long or the duration of inflation, right? Because আমি যদি জানি this n, which gives me the amount of time that this expansion happened, then I can tell you how long inflation lasted, right? So basically I need this, and you will see that this will be essentially a ratio of how much the Hubble radius shrank, right? Because try to understand this intuitively. If I can understand how much the Hubble radius shrank, and let's say I have some initial value of the Hubble radius and some final value of the Hubble radius, and if I can compare the two, I can understand how long it took for it to go from here to here, right? Does that make sense? So in that case, if I find a ratio of the initial Hubble radius at the beginning of inflation and the Hubble radius at the end of inflation, I should be able to tell you how long it took for this to happen, right? So that should give me an idea of how long inflation lasted. So in that case, we see that indeed this particular number of EFOs is defined as a logarithmic scale of the scale factor at the end of inflation depicted by AE and AI, which is at the beginning of inflation. Now, you might ask me why just A? Why the scale factor? Because as I know, the Hubble radius is given by the following, right? A and H. In fact, during inflation, H is constant. The physical Hubble radius is constant. Because remember, I wrote this from the Friedman equations that we have something like a relationship of the physical Hubble radius with the energy density like this. And you remember this from last class, right? So if rho is proportional to A naught, that means rho is constant. So if this is constant, this must obviously be constant because all of this is constant, right? So therefore, during inflation, the physical Hubble radius is constant. And if it is constant, that means it stays the same, right? So nothing is scaling the physical Hubble radius. So the only thing that I can work with when I'm dealing with an evolution is the scale factor, which is changing when it goes from a bigger Hubble radius and shrinks to a smaller one. So therefore, the duration of inflation should be given by this particular ratio of the scale factor. Because H I'm ekhane boshai, but it's not relevant, right? It cancels out anyway. Okay, so this is called the number of EFOs. And once you compute this number of EFOs, you will find Again, I'm skipping the derivation, but it's in my notes. So if you want to take a look, you can do that. You'll find that this gives you the following expression. Now, what is this? Okay. এখানে আমি কয়েকটা জিনিস বুঝতে পারছি from this expression of the number of ephors. একটা হচ্ছে যে it must be greater than 64. Okay. And this is a logarithmic scale. Remember that. And I have a logarithmic term of TR. Now this TR is called the reheating temperature. Now, what is reheating? Again, what is reheating is essentially this point in space and time. This is called reheating. And the reason why I didn't mention this before is because reheating is also devised as the end of inflation. Okay, so now we know what inflation is. So therefore, we can now understand what reheating is. And reheating is when inflation ends. Okay, so imagine what happens at the universe. Okay, এখন একটা broader picture আমরা চিন্তা করি. So we have an accelerated expansion time. So the universe is expanding at a very high rate, right? Accelerating. So there's a sort of boom that happens in the universe, right? And then all of a sudden that inflation ends. Of course, inflation ends at some point because we're not inflating as okay. We are perhaps accelerating now, but let's forget that for now because we don't understand that really well. But let's say radiation and matter domination time. Inflation did not take place over there, right? So therefore, this accelerated era must have stopped somewhere, right? And then generic expansion started. So ওই particular time যখন stop করছে from an accelerated boom, that particular time must have a lot of energy, right? And that particular energy is depicted by the reheating temperature, which is TR over here. Okay. Now, of course, this reheating temperature is essential to understand because this reheating temperature gives you an idea of the energy budget at the very beginning of the universe. And that particular energy budget is what made the universe evolve slowly, right? Because I mean, evolve if I don't have any energy, right? The universe expanded, so it had to use something to expand. And that something was this particular energy that was left from inflation. And that is depicted by the reheating temperature. And that is what formulates how long inflation lasted. Because it makes sense. Let's say I'm reheating temperature calculate. Let's say I can know what the reheating temperature is. So if I can know what the reheating temperature is, I can know what energy budget the universe has at that particular time, right? And if I can know what energy budget the universe has, I can sort of make an assumption what left that energy, right? Let's say if the accelerated expansion lasted for a longer time, I would have more energy, right? And if the accelerated expansion lasted for a shorter time, I would have lesser energy. So I can sort of make an assumption by assuming or understanding what reheating temperature is and make a relationship to how long inflation lasted. Right? Does that make sense intuitively? So that's why this is what formulates the number of ephors. Okay, and in fact, from this statement, for inflation to last long enough to solve the horizon problems and the flatness problems and give us the initial conditions of the universe, n has to be about 40 to 60 ephors. Now, if you're not familiar with cosmology, the reason why we call this ephors is because we have exponential expansion. Okay, so that's why these are like exponential terms. You have logarithm, so that's why we call it e-folds, okay? Exponential folds or whatever. So now, more or less, we have an idea of the model of the universe, right? So we had inflation, radiation, matter, and now whatever cosmological constant domination. So আপাতত মডেলটা বিল্ড করছি as in from fundamental perspective, but of course we need to understand the physics of it, right? What probes this inflationary period? What physics but physical mechanism is behind this particular era? So now let's look at the physics of inflation. And I'm doing an impossible task to study inflation in one lecture. It's very difficult, but I'm trying my best. So if you guys have any questions, I know a lot of these things are probably ambiguous, but please look at my notes, and there are many references that I will probably list down in the resources channel in our Discord server. So you can take a look. Okay, so to understand the physics of this early universe model, we of course need to understand how this early universe evolved, right? And a key characteristic of inflation is that the fact that we have one shrinking Hubble sphere, and we will see later on that every characteristic of inflation must also vary very slowly. Mathematically, we will see it in a bit, but we understand why it should vary slowly, because we need inflation to last an optimum amount of time, right? So if our dynamical objects that probes the physics of inflation varies very quickly, then we will not have inflation last enough, right? So we need them to vary very slowly. So key characteristic দুটা, একটা হচ্ছে shrinking Hubble sphere, which gives you the acceleration, right? And we need the objects to vary very slowly. So first, let's look at the fact that we have shrinking Hubble sphere. So again, taking the temporal derivative of the co-moving Hubble sphere and working it out. And let me reparameterize this. Actually, not reparameterizing, but just making a substitution of sorts by epsilon, where epsilon I'm saying is given by this following, where I can now reparameterize this with the physical Hubble radius h and n, which is the number of EFOs. Remember, from here, dn is essentially just d ln a, which you can see will be equal to hdt. Now you can do the calculations later on. Okay. So from here, if we have a shrinking Hubble sphere, which means that d by dt of AH inverse is negative, right? If that is so, then we must have epsilon to be less than 1. And from here, of course, epsilon has to be less than 1, right? So if epsilon is less than 1, this will be inherently negative, right? This term over here will be inherently negative if epsilon is less than 1, because this term would be positive. So it would save the negativity. And two questions now I can pose to you. That is, what happens when epsilon equals to 1? If you look at it from here, when epsilon goes to 1, this whole thing becomes 0, right? So what happens if it becomes 0? What does it mean? So this becoming 0 essentially gives you the fact that the evolution of the co-moving Hubble radius is 0. That means it's an instantaneous point where the Hubble radius is not evolving, right? So this must be some critical point, right? Karon, it's a derivative term, right? And a first derivative term, when it goes to 0, gives you a critical point. And that is something we know from basic calculus. So therefore, this must be a critical point. What is that critical point? This is exactly when inflation ends. Okay, maybe it's not very easy to see from here, but like we can take an understanding that, okay, we have the Hubble radius to shrink, where d by dt is negative. We have a point where d by dt is 0. And of course, it will again be positive, right? So this is the point where it shifts behavior from a shrinking Hubble sphere to an expanding Hubble sphere. And this is where inflation ends. Okay, because that is exactly where it stops shrinking, and then we have generic radiation matter domination, where the Hubble sphere again starts expanding. Okay, so we will see, in fact, further on that when we take a limit where epsilon goes to 0, as in for very small epsilon, this actually satisfies the dynamics of a particular set of geometry. And in fact, it makes H to be time translation invariant. And that is something that we can see head on, because remember what epsilon was? This, right? So if this goes to 0, then H dot must go to 0, right? So if H dot goes to 0, we know that H is constant. So when is H constant? It's during inflation, right? So I mean, for inflation to last long enough, we need epsilon to be very small. So that is one condition for inflation, okay? For inflation to, sustain. So in fact, when we have this particular condition, this satisfies a particular space-time called d sitter. Okay. Now this d sitter has line element or the metric. It looks like the following. So you see this exponential term on the spatial part? Fits in, right? Because we have exponential acceleration. Number one. Number two is that this d sitter essentially does not stop anywhere, right? If you look at this particular metric, does it have a point where it stops? But mathematically, does it, go to, can I say from here just by looking at it that it goes to, stopping the co-moving radius at any point? No, right? And in fact, if you've studied d sitter, you understand that d sitter space is essentially ever accelerating space, right? But that is not what we have for inflation, because inflation ends at some point, and that is for sure, because nailito radiation domination equal hoito na. So that's why inflation or the inflationary era is sometimes, or actually sometimes deemed as a quasi d sitter space. So quasi mane ki? It is, but not really. Okay, so it is almost like d sitter, but not really, because it stops. Okay, so these particular variables that I defined, epsilon, is called a slow roll parameter. And why it's called slow roll will be evident in a bit. But I can also define another parameter as such, which is given by kappa. And this is what tracks the evolution of epsilon. Okay, so that's why epsilon is called the first slow roll parameter, and kappa is called the second slow roll parameter. Okay, so why do we need kappa? Because we need inflation to last, right? So we need epsilon to be very small. So the evolution of epsilon, because obviously epsilon goes from, let's say, 0 to 1, right? At 1, inflation ends. So this variation of epsilon has to be tracked as well, because we need the epsilon to be varying slowly. So something has to track that evolution, and that is done by kappa. So kappa, in its definition, looks something like this, which tracks the evolution of epsilon. And I can write it as the following. Okay. So we understand that as long as epsilon is less than 1 and kappa is less than 1, then inflation lasts. And that is the condition we need. Now, done with the conditions and stuff, and how much time do I have? Okay. So we have an idea of inflation and all of that stuff, but we haven't defined again the dynamics, right? I'm not just supposed to say inflation needs to last. We define some parameters that makes inflation last, and so on. But we need to understand what's probing the dynamics of inflation, right? There has to be something that's causing this acceleration. From a quantum field theory perspective, we need something that, probes the physics, right? You cannot have empty space probing something so magnificent, right? You need a field, right? And that particular field is a scalar field called the inflaton. Okay, so anything that probes inflation which is a scalar field, is called an inflaton. Okay. So therefore, we now look at this particular scalar field and its dynamics. Okay, so remember when I was doing GR, how do we define any sort of dynamical system from GR? There's something that we do, like at the action, right? So we need an action that defines the particular system, and then we need to take a variation of that action, take the least action principle, and then find its equations of motion, right? So let's do the same for this dynamical system. So we define the inflaton as phi, which is the scalar field we're talking about, that probes inflation. And I want to put it in an FLRW metric. Now, you might ask me why I'm putting it in FLRW and not DC term, right? That's because this inflaton field does not only probe inflation, মানে এরকম না যে স্কেলার ফিল্ডটা হঠাৎ করে ভ্যানিশ হয়ে গেছে, যে ইনফ্লেশন শেষ হয়ে গেছে, scalar field or not. Of course, the scalar field still exists, right? So this scalar field does not only probe the expansion during inflation, but it also probes the expansion during the FLRW time. And in fact, more of the FLRW. So let me put it in an expanding space, I mean general, which is the FLRW. So if I put it in the FLRW and I want to write an action, I can write the action by its Lagrangian, right? So I can define the Lagrangian as follows. And the scale factor comes in because, you know, I have an expanding space-time. And the Lagrangian will have the kinetic terms and the potential. Okay. But as we know, the FLRW, let me just note this over here. So as we know from the FLRW metric that it has certain symmetries, right? We know it has homogeneity and isotropy. That means that any spatial deviation keeps the symmetry alive. That means any spatial deviation will still keep it invariant, right? So that means if I take spatial derivatives, they should go to 0. That means this term over here should go to 0, right? Because you see it's a gradient over the spatial indices. And therefore, the action boils down to the following. Just a kinetic term, which is a temporal derivative phi dot, and a potential term. Okay. Now again, the next thing I do is I take a variation of the action, and this will look like the following. Okay, and due to the least action principle, this will go to 0, which means this whole thing will go to 0, and therefore I will find something that looks like okay. So this is your equation of motion for a scalar field that is in FLRW. Okay. Now, what does this look like? Any ideas? You guys finished QFT, right? This is in fact the Klein-Gordon equation. And that is what we do, right? In QFT, for a Klein-Gordon equation, what do? We take a scalar field, we take the action, vary the action, equate it to 0, and this gives you the scalar field equation of motion. This is the Klein-Gordon equation, except we have a term that is not the same, right? And of course, it's not going to be the same because we included in FLRW, right? FLRW is an expanding space. QFT is done in flat space. So you do not have any contribution from the scale factor in QFT, right? However, you see that this extra term is a factor of H, which is a factor of the scale factor. So therefore, you have an extra term once you put it in FLRW. Okay? So now this particular term is called the Hubble friction. And we will see that this Hubble friction actually plays a pretty crucial role in inflationary dynamics. Now, next কাজ যেটা হচ্ছে অনেক কাজ actually is I need to find, what essentially probes the energy density of the universe, right? আমি একটা equation of motion পাইছি, but আমার of course বোঝা উচিত that energy density টা কিভাবে probed হচ্ছে. So I need to find an expression for rho. And let me call this rho phi because this is in case of the inflaton, okay? So of course, energy density will be an amalgamation of the kinetic energies and the potential energies, right? So I can write this as half phi dot squared plus v phi. Okay. Now note something. আমি কিন্তু এখানে v phi define করিনি. I did not define the potential, right? So every inflaton will have a similar kinetic term, which is given by this. However, in the way I define the potential will give me different models of inflaton, right? Does that make sense? So in that case, you can have many inflationary models just by specifying what your potential is. In fact, you can have an inflaton from string theory, right? Like the axion monodrome inflation model, which is an inflationary model coming from string theory. It's just by specifying the potential. You take the particular potential and then you put it in here and you can do the scalar field dynamics in the same. Okay. So whatever I'm doing right now is very general to any sort of inflationary model. Okay. Now, if I write this, and I know from the Friedman equation that this relationship exists, I can take a time derivative of this expression, and I can write this as, maybe it's better to take maybe I take a time derivative of the other one, this one. So if I take a time derivative of that, I will get second derivative of phi, del v by del phi times phi dot, and I can bring phi dot from the Klein-Gordon equation, which I wrote over here, and I can write this part as to be, 3h phi dot, right? Just, rearrange this. So basically I would have, if I rearrange this, I would have this, right? Which is essentially the same thing as this term over here. So I can substitute this part with minus 3h phi dot. And there's another phi dot over here, so this becomes the following. And if I compare this with the continuity equation that I gave you last class, which was, remember, from the covariant derivative of the energy momentum tensor, which was given by the following. Now, the subscript phi just means it's all for phi, the inflaton. So if I compare this phi dot with this phi dot, I see that I can devise an expression for pressure as half phi dot squared minus v. Okay. Now this makes me relate p and phi, because I have an expression for p over here. I have an expression for phi. Why am I saying phi? Rho. Sorry. So rho is the energy density. So now I can make a relationship of rho of phi and p of phi. Right? So in that case, this particular pressure will essentially determine the acceleration of the expansion. So I have an acceleration of the expansion that's happening during inflation, and this p will be particularly important when we're determining this acceleration of the expansion by this expression, which comes from the continuity equation. Okay, so from here we understand that p and rho, they are sort of related with the equation of state, right? Omega. And if indeed we have these expressions, from here I can sort of say that p is approximately minus of rho phi, right? If that is the case, that means that we have negative pressure, right? And if we have negative pressure, this inflaton with negative pressure now acts like the cosmological constant that accelerates the universe. So it amra kemne jani, because now we have an accelerated expansion phase, right? We have a cosmological constant that actually has negative pressure, and we also had a similar type of a cosmological constant that has negative pressure in the very beginning, right? So that means you can now move towards, saying that maybe there is some theory that relates the two. Okay, so now this inflaton can act as a temporary cosmological constant that sources the accelerated expansion during inflation. Okay. Now, we're not done. Now, next কাজ যেটা সেটা হচ্ছে যে আমাদের এই পার্টিকুলার ডাইনামিক্সটাকে লাস্ট করতে হবে. We need it to last, right? We need inflation to last long enough so that it solves the problems of Big Bang cosmology. So therefore, we now get introduced to slow roll inflation. And slow roll inflation, and in fact, inflation has to be slow roll because we need, again, inflation to last at least 40 to 60 folds, right? So we need the inflationary model to be slowly varying, which is why it's called slow roll. In fact, it will be evident in a bit as well. Now, the proper dynamics of inflation will be determined by the combination of the Friedmann equations, right, which is the solution of the Einstein's field equations, and also the Klein-Gordon equation that we have solved right now, because that is also an equation of motion. So therefore, two equations that is important for the dynamics of this particular era is the Friedmann equations, which is given by the following. And particularly, I can write it in terms of phi dot and v, and the Klein-Gordon equation that I just found out, which is the equation of motion of this particular scalar field, right? So these equations are coupled for sure because I have similar terms and they're dependent on each other. So therefore, I need to understand the precise conditions that lead to this particular inflationary stage, right? So for that, I need to understand what these two equations can do. So now, note that these two equations can actually be combined into an expression for H dot. So I mean, দুটো equation use করে, I can write an expression for H dot. And this will be equal to minus half of phi dot squared by implied squared. Okay. And taking the ratio of the two equations above and the expression for the, H dot, I can write the slow roll parameter, the first slow roll parameter epsilon, which was H dot by H squared, right, as half phi dot squared by m Planck squared H squared. I can sort of do a little bit of algebra, and this is what I find my expression to be. Okay, now let's take a look a couple of minutes into this expression. Okay, what is happening? So I have a phi dot squared up in the numerator and half phi dot squared plus v phi in the denominator, right? But now remember that for inflation to last, epsilon must be very small. So this should be very small. That means that this should be small, right? And if this is small, which is a phi dot term, this term should also be very small. That means that we are probing a certain dynamics where the potential is dominant, not the kinetic term. So that is why it's called slow roll, right? Because you have very small kinetic terms, that means let's say the inflaton is rolling very slowly because it does not have a much kination. Okay, that's why this is called slow roll inflation. So that is the case. I can sort of make this assumption that if indeed the kinetic term is small, that means the acceleration of the inflaton must be very small as well. Remember, don't confuse acceleration of space with the acceleration of the inflaton. They're two different things, okay? Space is accelerating, okay, very much. But the acceleration of the inflaton is slow because the kinetic term is small, okay? So that means acceleration of phi is small, and for that I can sort of define a dimensionless acceleration parameter, which is given by delta, which essentially measures or basically relates the acceleration of the inflaton. And over here, remember, this is the friction term that comes from the Klein-Gordon equation that I have written over here. Okay. Now, so of course, if the acceleration of phi is small, then delta must be also very small. So this is a very small quantity as well. So putting the two together, I want to sort of formulate the theory in regards to the potential, because remember the potential is dominant here, right? So একটা পয়েন্ট হচ্ছে যে পোটেনশিয়ালটা ডমিনেন্ট, তো তার মানে হচ্ছে যদি আমি থিওরিটা পোটেনশিয়ালের সাপেক্ষে যদি আমি ডিফাইন করতে পারি, then it will be greatest because of course the potential is dominant over here, number one. Number two হচ্ছে যে পোটেনশিয়ালটা কিন্তু জেনারেল, right? So তার মানে if I can devise the theory in terms of the potential, I can just specify my potential and then just calculate all variables of the theory, right? So let's say I have some potential for a particular theory, I plug that potential in, my theory is 2 minutes. Okay. So basically the point is that if you specify the theory in terms of potential, then it gives you a lot of ease to compute for different types of specifications, right? You know what I mean. So in that case, I'll just skip derivation, and eventually what we will get is the slow roll parameter in terms of the potential. Now I'm really sorry because I don't have time, but I really want to show this. However, these are on my notes, so you just can take a look at the derivation if you're confused. So after doing all of the calculations, taking the limit where phi dot is much less than v phi, you will be able to devise the slow roll parameters in terms of the potential only. Okay, so you will see that epsilon in terms of the potential will be defined as the following, where v comma phi is essentially just the derivative of v with respect to phi. Okay, and you can also devise another slow roll parameter, which is a function of the delta parameter that I wrote over here and the epsilon, which is given by eta, which is also in terms of the potential, and this goes as the second derivative for the potential. So this essentially is just okay. So now what you have is a test. If indeed whatever inflationary model you're working with, if it works and if it abides by the slow roll conditions, that means it is a viable theory to explain the early universe. Okay, so that means you plug in any sort of potential that comes from string theory, basic cosmology, or even alternative theories, you will get the potential, plug it in over here. If it abides by these two particular conditions, that means it's slowly rolling and it can explain the acceleration of the universe during its very beginning. Okay, so that means that particular theory is viable. And I guess that's it. Any questions? Real. Okay, the reason why I smiled at this is because remember cosmology underlying framework is GR, right, which is the gravity theory. Can you quantize gravity? Well, for that you need to go through alternative theories like string theory and so on. So আমি directly বলতে পারবো না যে এই particular fieldটাকে আমি হচ্ছে condense করতে পারবো না কিনা, particularly এখন for this it's a classical